Okay. Chapter 13 and 14 are about mixtures, solutions, and how they behave. Okay. So, a solution is a homogeneous mixture. Homogeneous. Okay. The prefix homo, what does it mean? Same. So when they say homogeneous, that means the same all the way through. No matter where you take a sample, you're going to see the same, you're going to get the same pieces every time. That it's mixed molecule by molecule. That there's no clumps of pieces. That's what makes it a solution. And if it's mixed in an aqueous solution, you can tell by looking how well it's dissolved. If it looks cloudy, you haven't dissolved it, right? You see stuff sitting on the bottom, you haven't dissolved it. If it's evenly colored all the way through, you've dissolved it, right? Okay. Actually, we're going to talk mostly about things dissolved in water, but they can really occur between any states of matter. You make states of matter in all kinds of solutions. Like the most common example is a solid in a liquid, like Kool-Aid. I put the solid sugar into the liquid water. You can mix two liquids. For me, and I wrote this because of my background. An example would be antifreeze. Actually, here in California, we would call it coolant for your car. It's the same stuff, and it does both jobs. It's the stuff you pour in the radiator. But if you pick up that jug at the auto parts store and just pour it straight into your radiator, it won't work. It won't work as well. The instructions tell you to mix it 50-50 with water. If you don't mix it, it doesn't work. Somehow mixing it changes the temperature it boils at. We'll talk about that later. That's one of the properties we need to talk about. The air we breathe is a mixture of nitrogen, oxygen, a little bit of carbon dioxide, a little bit of argon, a little bit of BO. Okay. Are there chunks of oxygen in the room? Have we seen any chunks of oxygen? No. Okay. You can think of our alloys as a solid dissolved in a solid. So brass or any alloy, any mixture of metals. A liquid dissolved in a gas, that describes water vapor. Water vapor is a liquid, water, dissolved in a gas, the air. So the humidity in the air is a liquid dissolved in a gas. Okay. You can have solids dissolved in gases. You can have gases dissolved in solids. All 9 possibilities exist. It's just a matter of how well things are mixed. Now, like brass, you don't make the mixture while it's solid. You make the mixture while it's a liquid, but it's still a mixture when you cool it off. That make sense? Okay. So when I mix something, I'm not changing where any electrons are. So the example I like to use for this one is, in order to make Kool-Aid, I need to mix water, sugar, and red powder. And when I'm done, so I've mixed something wet with something sweet and something red. And when I'm done, I get something that is wet, sweet, and red. Did I make anything new by making Kool-Aid? Okay. So that means it's not a chemical change, it's just a physical change. I didn't make anything new when I dissolved it. Okay? So I can separate it back out. All mixtures can be physically separated. Physically means that you can separate them without making anything new. I can take the water out of Kool-Aid. I can take the sugar out of Kool-Aid. I can take the red out of Kool-Aid. It's a pain, but you can do it. I mean, if I had a mixture of sugar and water, how could I end up with separate piles of sugar and water? I could boil the water, catch the steam, right? The sugar would stay behind. So I started off with something that was sweet and wet, ended up the wet separate from the sweet. Didn't make anything new. But when you read this, when people read this, they say it's easy. They think that it says can be done with physical means. That implies that it's easy to do. No, that doesn't mean it's easy to do. It means that you can do it. It's possible. I mean, how would you get the red out of Kool-Aid? If you boil the water, you've got sugar and red stuff mixed together. Right? How are you going to get the red away from the sugar? I don't know. Actually, I do know. What you'd have to do is, the way I would do it would be using the fact that the sugar molecule is heavier than the red molecule. So it's going to effuse, it's going to spread out faster. So if I put a piece of paper and soak it up, the first water that comes out will be the stuff with red in it. And I'll be able to take that red off of it. Just cut the paper. And then the stuff that's left behind will be where the sugar's at. It's called chromatography. You may have done it in your biology class. But that's how you separate it. Or see how fast it effuses. It actually diffuses as a solution. Because the sugar is going to be moving slower than the red stuff. Because the sugar's heavier than the red stuff. Okay? Hey, got to define some terms. Solvent, the stuff that does the dissolving. That means if they're different phases, it's the one whose phase you end up in. Solute, the stuff that's dissolved. So in Kool-Aid, what is the solvent? Water. What is the solute? Sugar and red stuff. There's two solutes, right? Or as long as you're drinking red. Okay. But what happens if I pour two liquids together? I pour together some water and some alcohol and pour it together and shake it up. And they mix. Which one's the solvent? Did the liquid dissolve in the alcohol or the water, or did the water dissolve in the liquid? The answer is they dissolved in each other. So actually, we don't use the phrase solute and solvent. If we wanted to, it'd usually be based on how much stuff there is. There tends to be more of the solvent. But actually, the term we use is miscible. I think every time I see this word, I think they got the C and the S backwards, because it should be mixable. Miscible. So they dissolve each other. So there's not really a solvent and a solute. They just mix together perfectly. Well, I put together oil and water. They don't mix because the water can't hang on to the oil. Right? So I need a word that's the opposite of miscible. So they got very creative, came up with immiscible. They didn't do unmissable. And you understand that when it should be IN, but they change it to an M when it starts with an M. Because ever tried to pronounce NM together? Immiscible. It's a pain. So oil and water are immiscible. Vinegar and water are miscible. And most of our time is going to be spent talking about aqueous solutions. And we saw this word aqueous before. What did aqueous mean? We wrote it as AQ. Yeah, see the aqua in there? Dissolved in water. Okay? And what water can dissolve is ionic solids and polar solids. That's because water is very, very polar. It's got charged ends. Ionic solids have charges. Water can hang on to them. Polar compounds have partial charges. Water can hang on to it. So the rule is like dissolves likes. Things with charges dissolve things with charges. Polar dissolves polar and ionic because things with charges dissolve things with charges. They can hang on to them. Those charges allow that attraction that you need in order to make them tear each other apart. Nonpolar dissolves nonpolar. So things without charges dissolve things without charges. And the reason why is because London dispersion forces aren't affected by what you're next to. How hard you're stuck to your neighbor is all about how the charge, that temporary partial charge that moves around. That's how gasoline sticks to gasoline. That's how oil sticks to oil. So when I mix gasoline and oil for a 2-cycle engine, the oil and the gasoline hang on to each other just as well as they hung on to themselves, because they hang on exactly the same way. Using London dispersion forces. Temporary, partial, instantaneous charges, changing their neighbor to have temporary, partial, and instantaneous charges. Okay? But if I put oil and water together, oil and water don't mix. And they don't mix because the water wants to hang on to the water. That's the whole reason. Not that the oil wants to hang on to the oil. The water hangs on to the water, and any oil that gets in between two water molecules is going to get pushed out of the way so that those water molecules can come together. You may have seen it if you ever sprinkled water on a freshly waxed car. And it beads up. You get little beads of water that run off because the water can't attract to the wax on the car. So it attracts to itself. You get little beads of water that roll off really fast. Okay. Every time you mix something, you don't get a solution, though. You can mix stuff and not get a solution. Heck, we had precipitates that settle down to the bottom. If you got a solid that's settling down to the bottom, is it mixed evenly? Molecule by molecule? Nah. Okay. Come into 3 categories if they're not solutions. The first one is called a suspension. When things are suspended, they're just hanging there. Something's holding them up. They're hanging there. And when the things that are hanging there, it's only a temporary thing, and they're going to slowly settle out. We're talking about things like you grab a container full of river water. It looks cloudy when you first get it. You set it down. It'll turn clear with a pile of stuff on the bottom. The fact that pile of stuff falls to the bottom means it's a suspension. Okay. Why? Because the particles are bigger. It's not individual molecules, it's hundreds of molecules. And hundreds of molecules water can't keep a hold of. They sink down to the bottom. And since it's hundreds of molecules, you can separate them by filtering. You put a filter in the way, it's going to catch those particles. Because the filter has a mesh, the big particles are going to get caught on top of that mesh. Much like how I make coffee in the morning. I throw the coffee grounds on top of a filter. The water goes through. Some of the stuff dissolves and some doesn't. The lovely brown nectar that flows from the bottom of the thing is a solution. All those coffee grounds up top don't get through because they get caught by the filter. When I was growing up, they didn't have drip coffee makers. You percolated coffee. You threw coffee into a pot and boiled it. Okay? And what you'd have to do is you'd have to wait for the coffee grounds to settle down to the bottom. Because you tried to drink the first cup of coffee off the top, you get chewy coffee. Gotta wait, give it some time, it'll settle, or stick a filter in to catch it all. Okay, 2 ways to separate it. Colloids are bigger than a solution, so more than one molecule, but they're smaller than a suspension. So they're not maybe tens of molecules instead of hundreds of molecules. And they don't settle or filter. Well, if they don't settle or filter, isn't that a solution? We'll see why it's not. There's a test that shows why they're not a solution pretty quickly. The third word they use is an emulsion. An emulsion is just a special kind of colloid. It's a colloid of a liquid in a liquid. It's two liquids colloided together, where they don't quite mix molecule by molecule. There's chunks of one liquid and chunks of the other liquid just next to each other. So how do we check if it's a colloid? Well, it's something you guys do all the time. You look at it. You look at it, and if you put a beam of light through a mixture, okay, and that's what this picture down here is trying to show, is there's 3 kinds of mixtures here. Notice how you can see the beam of light in the first one, right? Can't see the beam of light in the second one, but that same beam does show up in the third one. So the light is going through the blue stuff, but you can't see it there. That's because the middle one, the blue one, is a true solution. It doesn't have any big pieces. Individual molecules cannot stop light. The other 2 interact with the light, so you can see something's going on. That's the Tyndall effect. Okay? You will see light reflecting off any undissolved particles. So in a solution, there's no Tyndall effect. You can't see the beam. Can you guys see the beam between the projector and the screen? You can't see it. That's because air is a solution. We don't have big particles that could block the light. But It's hard to see because this room is pretty bright. Have you ever looked up in a movie theater? What do you see when you look up in a movie theater? You see little sparkles up there, right? Those little sparkles are pieces of dust. So that those pieces of dust, when you turn off the fan, they're all going to settle down to the bottom. The dust is a suspension. So if you have a suspension, you're going to see sparkles off the big pieces. And in a colloid, the pieces are medium-sized. They're too small to see individual particles, but the light's still going to bounce off, so it'll look like a continuous beam. You'll see a continuous beam all the way through it. So, well, I could use some other examples. When you're in a car at night, from inside the car, can you see the headlights of your own car? Can you see? You can see where they hit. Can you see between your car and where they hit, where the light head things are? Well, the answer is sometimes. On a clear day, no, you can't see it. Air is a solution. But on a rainy day, you can see the drops of rain go through the light bulb, right? That's because rain is a suspension, and it's not staying mixed very well. Big chunks are falling down. Okay? Then the fog. What happens to your headlights in the fog? You see the continuous beam off to the side, right? In fact, you got to turn your headlights down because it bounces so much off the fog, it blinds you. You can't see what you're doing. Okay? Fog is a colloid. Little tiny drops of water. When those little tiny drops of water run into each other, they turn into big drops of water, and that's how a cloud turns into rain. So I see with things from the sky, you can see those. So in a solution, well, technically, I could turn the light on, and all you'd see would be a dot over here. You wouldn't see it along the way either, right? But the fact it goes through without being seen, solution. Colloid, you're going to see the continuous beam, like looking at the a car from the side at night in the fog. And a suspension, there's probably still going to be some small particles there, right? But then there's going to be big ones that are going to sparkle. So I can tell a difference between a suspension and the other two because the suspension filters. But if I really want to identify which of the three it is, I need to look to see what kind of the Tyndall effect. Yeah. It depends on how big the pieces are, okay, and how good your filter is. Yeah, mostly, did it have big enough pieces the filter to catch them all, or not? And oh, here's one. I'll give you an example of an emulsion. Milk. Because, oh no, is milk an emulsion? Well, probably the milk you drank is an emulsion. Any milk you drank is probably an emulsion. But when you get it from a cow, it's a suspension. Because if you take a cow's milk straight out of the cow and just let it sit, the milk fat in the milk will rise to the top because it's nonpolar and less dense. If you skim off that fat, you have skim milk. Okay. Why? Well, because that those fat pieces are big globs of fat when they come out of the cow. And they run into each other and stick together and rise to the top. And if that stuff you take off is called cream. And if you stir it real fast, you can make whipped cream. And if you keep stirring whipped cream, you'll get butter. You never want your whipped cream to go to butter. Okay? But say, well, anybody ever experienced the fat rising to the top the milk from a grocery store? Why don't you see it? Because if you read the bottle, read the container, it says homogenized milk. Homogenized, same. They take that milk and they stir it vigorously, enough to break the fat molecules into little tiny pieces, small enough that they stay separate. So they turn that suspension, where the stuff floated to the top, into a colloid. And we know it's a colloid because it doesn't separate if I let it sit. And but there's a solid in there that stops the light from going through it. So the fact that you look through it and it doesn't look clear tells you that there's solids in there someplace, or bigger molecules. Could be a colloid, could be a suspension. You got to filter it to tell the difference. Make sense? Okay. So how do they dissolve? What's going on when things dissolve? The process is called, creatively enough, solvation. Okay. So water is polar. It's got a positive end, it's got a positive side and a negative side. So the negative side of water is going to be able to come to the positive ion. It's going to be attracted to it. And the positive side of water is going to be attracted to the negative ion. So that means the water can pull on those ions and pull them off. And then once it's pulled them off, it can surround them and carry them away. So I'll show you a couple of diagrams. One I drew and then one done by professionals. Okay, so this would be a crystal of an ionic compound. Regular, repeating, positive and negative ions. Okay, water comes in. And for water, the oxygen is negative because it's got the higher electronegativity. So the oxygen end of the water molecule is negative, partial negative. It's going to be attracted to the positive piece. The hydrogen side is positive. It's going to be attracted to the negative piece. But, excuse me, Mr. Green, everything in the ionic compound is a full charge. And water is only pulling with a partial charge. Shouldn't the full charge win? Doesn't it make sense that partial charge wouldn't be strong enough to do it? Well, one-on-one it's not. But water gets to team up and surround those pieces. So it's multiple water molecules pulling. Okay? And they surround the negatives with H's. They surround the positives with O's. And that way they can carry it away. But that's going to make a limit on how much you can dissolve. You see how this makes a limit? Eventually you're going to add so much stuff that you don't have enough water molecules to hang on to it all anymore. And then the stuff just piles up on the bottom. Because it's really a tug-of-war between the crystal and the water. And if it dissolves, the water's pulling harder. If it doesn't dissolve, the crystal's pulling harder. By pulling, I mean attractive forces. The intermolecular forces are stronger in the crystal than in the solution. Okay? So that was me drawing it. Let's see if I can find something done by professionals. Okay, you put some salt in water. Stir it up, it disappears, right? It's not cloudy. Why? Let's zoom in. They videotape themselves zooming in. Okay? What you have there is salts. You see how the red oxygens are attracted to the positive pieces, and the gray hydrogens attract to the negative pieces. And that's how salt dissolves. Okay? So that difference in electronegativity and the shape make it polar, so it can do this. Something without charges can't do this because it can't hang, all it can use is London dispersion forces and the charges are stronger. Make sense? Okay. So you saw that. Okay, so it's a tug of war. Solids will dissolve if the attractive force of water is stronger than the attractive force of the crystal. Because remember, we had a whole list of things that did dissolve and didn't dissolve. We talked about double replacement reactions. We had to figure out whether we were going to make a solid or not, because if it made a solid, it happened. If it didn't make a solid, it didn't happen. Well, this is not going to make a solid, because the attractive force of the water molecules is stronger than the attractive force inside that crystal. Okay. So solids will dissolve if the attractive force, if water wins, it dissolves. If the ions win, it doesn't dissolve. And the things that don't dissolve in water we call insoluble. Not able to be solution. Soluble, able to be solution. So it's not soluble, it's soluble. So we're talking about solutions. So that's what happens in an ionic compound. What other kinds of things can water hang on to? Well, it's got charges, so it can hang on to things with charges, polar. The things it really dissolves well are things that can hydrogen bond. Because that gives water a great place to hang on to them. Ever tried to see how much sugar you could dissolve in water? It's an amazing amount. Okay? Why? Well, because we always write the formula for sugar is stuff like C6H12O6. Well, in this, the carbons are all in a line. I don't have room to make them all in a line. And then coming off each one of those is an OH. So there's always lots of places for water to hang on because each of those places where it's an OH, they can hydrogen bond. And then the rest fill up with H's. The last one's got a double bonded O. So with all those OHs, lots of places for water to hang on. Oops, that should be an OH. Sorry. Lots of places for water to hang on. So you can dissolve a lot of sugar in water. Okay. Now, other polar molecules can do the same thing. But they usually don't do it as well as water because water's charges are bigger. And it's the fact that water's polar and can dissolve so many things is why we look for it. We're looking for life because if we can't get things to dissolve, we can't get them to touch each other. If they can't touch each other, they can't react. So when they're looking at other planets looking for water, because that's the only way they can see how the pieces can get together in order to make life. In other words, make chemistry happen fast enough so you'd have life. So molecules that can hydrogen bond are very soluble. Like sugar. So remember, to hydrogen bond, they have to have the oxygen hooked to hydrogen or fluorine. But that only happens in HF or nitrogen. Okay. And electrolytes, we've talked about before. Substances that conduct electricity when melted or dissolved in water. And we've talked about these before because we call them ionic compounds. Because remember, conducting is charged pieces moving. The ones that have fully charged pieces are ionic compounds. Because what happens to ionic compounds when they dissolve? They fall apart into ions. Okay. Some questions out of the book about these. Okay. Talk about some bizarre things about electrolytes tomorrow to start off.